Okay, hello everyone. My name is Yanming Zhang, and this is recording of my master defense at ETH Zurich. During the year of 2024, I did my master thesis with the title Neuromorphic Devices Based on Ferroelectric and Molten Oxide under the supervision of Professor Bing Laos from Department of Electrical Engineering and co-supervised by Professor Nicholas Baldin from Department of Materials. And here's a brief outline of my presentation. During the past year, we studied the neuromorphic devices by mainly two aspects. The first aspect is on materials. We want to try and investigate the hybrid heterostructures of ferroelectric and molten oxide. So we did a lot of things on the device design and we encountered some materials challenges, leaving us some open questions. And the second aspect is what we want to explore the optimal device design for ferroelectric tunnel junctions. To do this, we choose our major technology using tungsten oxide as a bottom electrode, and we explore the scaling and shape effect, and we investigate the ferroelectric switching and different time scales, and finally touch to the co-integration of tunnel junctions and capacitors. Firstly, to introduce the motivation and background of the research work done in our group based on neuromorphic computing using ferroelectric memoristors, I want to start with a story. Personally, I'm a big fan of Go. Go game is an Asian game that's popular in some Eastern Asian countries like China, Japan, and Korea. It's a super complicated game that the average, the possible board configurations of an average Go game is surprisingly high, just like counting the number of stars in the universe. So for decades, it was regarded as a great challenge for computers. And I remember when I was a child, I could easily win the computer when playing the Go. However, things were different when I was in high school. In the year of 2016, there was a breaking news that a legendary Go player, DeSoto, was challenged and beaten by an AI program called AlphaGo. The AlphaGo relies on deep neural network to learn thousands of human games and become very strong, just like the saying, deep learning is killing every problem in AI. But actually, at that time, some Go fans, including me, would say that version of AlphaGo is good but not very stable. So at that time, we still believe that AlphaGo could be defeated by younger and more talented human Go players. 1 year later, Ke Jie, the number one human Go player at that time, was challenged by AlphaGo and he was defeated ruthlessly. And he was crying during the game. It was really a sad story. And this is because in that year, there was a new version of AlphaGo developed called AlphaGo Zero. Given by its name, it learns from zero and trained by playing against itself. So it seems that there's no need to learn from human knowledge anymore. And here comes the question, should AI still learn from human brain? Technically, probably no, but biologically, yes. Considering the power consumption of AlphaGo Zero, it is very energy hungry to run so many CPUs and GPUs and do the vector matrix multiplication in the digital domain. But as a human being, we just need some food and drink, and the power consumption of our brain is exceptionally low. In fact, we have to learn from our brain with biological neural network to make this computation more energy efficient. And here's the idea of neuromorphic computing or brain-inspired computing to really mimic the computing architecture of our brain and to do the vector matrix multiplication in the analog domain. And this requires a crossbar array of memoristors. And basically, the matrix elements are implemented in crossbar arrays of memoristors, which can switch the resistance depending on the IV history, serving as synaptic weight. And basically, here are some examples of the computational memory devices based on different physical working principles, like the formation of conductive bridges or the phase-changing materials or the spin torque for magnetic tunnel junctions or the ferroelectric polarization for ferroelectric devices. They all have some pros and cons, but just in terms of energy consumption, according to some benchmark tests, the ferroelectric devices might be the most energy efficient one. And typically, the ferroelectric devices could be used as different components in neuromorphic engineering. And there are mainly three types: the ferroelectric tunnel junctions, FTGs, and ferroelectric field effect transistors, FEFAS, and ferroelectric capacitors, FE-cap. Typically, FDGs, ferroelectric tunnel junctions, which relies on the quantum mechanical tunneling through an ultra-thin ferroelectric layer. And basically, the screening of polarization charges could effectively modulate the potential barrier. And thus, we can modulate the probability of quantum mechanical tunneling by applying external electric field. And similarly, for FEFET, field effect transistors, it also leverages the polarization charges of that ferroelectric gate electrode to modulate the resistance of the semiconducting channel underneath. And finally, for ferroelectric random access memories, it composed of a transistor connected to a capacitor to store the polarization charges. Next, in our group, we are working on the neuromorphic devices on materials level and on device level. And typically, during my master thesis, in order to develop highly functional memristors, we want to answer the two questions separately. The first question is on materials. We want to co-integrate a ferroelectric oxide, HCO, and the malt oxide, VO2, together. But we are new to VO2. We don't know how does it interact with HCO, so we have some challenges on materials. In terms of materials, the ferroelectric oxide we are studying is hafnia. And for decades, hafnia has been used as high-K dielectric material in semiconductor industry. But only 12 years ago, ferroelectricity was observed in hafnia thin films. And according to the crystal structure, the polarization is only possible in the orthorhombic phase, which is metastable and non-centrosymmetric. And there are many approaches to stabilize the ferroelectric phase, and the most common approach is making solid solutions with zirconia. And according to the phase diagram, the admixture of hafnia and zirconia, HCO, could be crystallized into the ferroelectric phase with a stoichiometry of 50-50. Where it shows the largest polarization. Typically, instead of making solid solutions, one most recent approach is to making HCO superlattice, which is an alternative stacking of hafnia and zirconia atomic layers. And typically in our group, we focus on the HCO superlattice in this work because it could potentially offer high temperature stability and polarization. Next, the malt oxide we choose to study is vanadium dioxide, VO2, which is a strongly correlating oxide and could undergo metal insulator transition at around 60 degrees Celsius. And previous research work shown that this metal insulator transition could even be driven by gate electric field, even at room temperature. And the recent work at ETH Zurich demonstrated that this resistive switching in VO2 memristors could be triggered by picosecond ultrafast pulses with ultra-low power consumption down to femtojoule per pulse, which makes it promising at memristors. And typically in our work, we want to integrate the vanadium dioxide together with the HCO superlattice to make highly functional memristors leveraging the ferroelectric field effect and the metal insulator transition or malt transition together, and to study the interplay between the two. So probably with the polarization, we can study the malt transition or the other way around. Probably with the malt transition, we can also affect the screening of polarization charges. To study this, we designed several devices. For the capacitors, the HCO here could be polarized into the ferroelectric phase, and the VO2 here serves as a bottom electrode for the capacitors. And we also designed some field effect transistors. Similarly, the HCO here could be polarized into the ferroelectric phase by the gating effect, and we are studying the conductivity of the VO2 resistant channel. For these field effect transistors, we also designed some gated hotbar structures shown here to allow for investigating the magnetotransport properties. Basically, in presence of a strong magnetic field, the charge carriers will be deflected into the edges of hotbar, resulting in a Hall effect. And the Hall effect is very useful to understand the transport properties like the carrier mobilities and carrier densities. And it is also very interesting to understand the magnetic properties of VO2. To achieve this, here's our mask for UV lithography. As you can see, we have several blocks of devices and also some test structures on the top to check the ferroelectricity of HCO. And all of the devices could be measured from the top. And in order to have a better understanding of the VO2, we also design some lower level structures like the level 2 structures with much bigger platinum pad so that we can measure during the processing stage without finishing the whole structure. Materials-wise, we got the vanadium dioxide samples from two different sources. Our collaborators from KU11, they grown the VO2 by oxygen-assisted molecular beam epitaxy, which is a dry technique. And our partners from IBM Zurich, they focus on the atomic layer deposition, ALD, which is a more chemical approach and the wet technique. Next, to compare the two sets of samples, we did some electrical measurements. As you can see, the MB ground VO2 is much more resistive and close to the reported value for VO2 thin films. And it is also more robust during the microfabrication stage and survived after liftoff. While for the ALD grown ones, they are far less resistive, probably because of some organic or proton residuals. And we also encountered some fabrication issues during the processing. So we decided to just proceed with the MB VO2. With the MB ground VO2, we can then deposit the HCl superlattice and a tungsten layer on the top. And we can then anneal the chip and pattern the HCl and define the tungsten top electrode. And with this structure, we can perform some very simple double IV measurement to check the ferroelectricity of that chip. However, according to the IV curves looks very leaky and not ferroelectric at all. And actually, there was also a control chip without the VO2 in the same run of HCO deposition, and it is indeed ferroelectric. So there should be something wrong induced by the VO2. To explain this, our hypothesis is there might be an oxygen scavenging effect of the VO2 bottom electrode. And this is based on our knowledge from a known system using tungsten oxide as a bottom electrode. Basically, the tungsten oxide could supply some oxygens into the region of HCO layer, and after annealing, the HCO superlattice will be crystallized into the orthodontic phase and the ferroelectricity is stabilized. So if this works, probably the opposite scenario happens in terms of VO2, that VO2 could scavenge some oxygens from the HCO region to form a more stable phase like V2O5 or VO3. And as a result, there will be some oxygen vacancies left in the region of HCO, and the HCO will be crystallized into the tetrahedral phase, which is not ferroelectric. To test this hypothesis, we decided to make another chip by introducing an alumina intermediate layer to block the oxygen transfer between the VO2 and HCl superlattice. In principle, the oxygen scavenging effect could be kind of solved. However, for the results, we indeed reduce a little bit of the leakage, but we are still not ferroelectric yet. Here one can conclude on the material, and what we could do next is to add some tungsten oxide as an oxygen supplier layer. And PhD students in our group, Anvisha and Alex, will take this over to do more experiments like temperature-dependent measurement or XRD characterization to identify if the VO2 changes the phase or not. In parallel to the research we did on materials, we also wanted to learn more about the optimal design for ferroelectric devices like ferroelectric tunnel junctions. And we decided to learn this on a much known system, which is HCl superlattice on tungsten oxide. To achieve this, we started with a parameterized mask design. Basically, we know how to make ferroelectric tunnel junctions with tungsten oxide, and we know how to process micrometer scale devices, but we have never scaled the FDGs down to submicrometer scale with E-beam process. Here is an FDG, and only the tiny area under the MESA is the functional area for quantum mechanical tunneling driven by external electrical field. And we are questioning if the shape of this functional area matters. And with parameterized mask design, we could generate a large amount of devices with different sizes and different shapes, like circles, stars, and octagons. With this very compact design, we can do automatic mapping measurement as a probe station by controlling the motion of the needles to get really a large amount of data for devices with different shapes and sizes from 30 microns down to 0.6 micrometer. Here are the results for mapping measurements. we have plots of current density in log scale as a function of voltages for devices with different sizes and shapes. The curves looks very noisy because we have already hit the range limit of the SMU, and especially for small devices, so there will be a severe charging effect due to the long interaction time of the SMU equipment. But what we are actually interested in is this memory window here. There are two current states, the on state and off state, and we wanted to know the off ratio between the two states. Here is a plot of on and off currents with respect to the nominal area calculated based on the size and shape of each device. And as we can see, the separation between the two lines defines the off ratio. What we could find is, for very large devices, the dispersion of data point is very linear. However, the off ratio, which is the separation between the two lines, drops while scaling down. Comparing with the stars, whose off ratio is not very good for small devices, stars and some octagons still show very decent off ratio while scaling down. So we're wondering if there's something to do with electrical field distribution. To further study this, we design more measurements. If we go back to this slide, from the application point of view, in the crossbar array of membristors, we compute the vector matrix multiplication, and we want to store this synaptic weight in multi-level memory by the conductance of the device. For this reason, we wanted to see if we can program the synaptic weight in different conductance levels of a single device. Another thing is, compared to the biological timescale, which is usually in milliseconds and pretty slow, but with our CMOS-compatible neuromorphic hardware, we can do the resistive switching at a much faster timescale, down to nanoseconds or even picoseconds. So here the aim is to program the conductance or synaptic weight at different timescales. In order to program the synaptic weight, we design the experiment this way. Firstly, we can apply a programming pulse or writing pulse with controllable pulse width, then followed by a very small IV swab to raise the resistance in a non-destructive way. Then we can increase the pulse amplitude in constant steps and read again and again and eventually form a double IV swab to study the hysteretic behavior of ferroelectric switching. This read and write measurement is also more accurate and can alleviate the charging effect. Here is one of the main findings we got from this read and write pulse measurement. We can see the hysteresis from this double IV measurement. On the same device, we vary the pulse width from very slow to very fast pulses, and interestingly, there's a shifting of the resistance level. Another open question is, we found a step-lag feature, and this jump in resistance is only observable at fast pulses. We have never seen this before. Our understanding is, together with the ferroelectric switching, there are some ionic contributions. So probably the ionic conduction is a relatively slow process, so we can see this step at ultra-fast ferroelectric switching. Compared to our previous work that we have an on-off ratio of only 1.8 on HCU superlattice at 20 nanoseconds. Here we have a more decent on-off ratio around 8 at 20 nanoseconds, thanks to the scaling. We can also compare the shapes by these pulse measurements. Here we plot the R times A as a function of the writing pulse amplitude. Basically, the product of resistance and nominal area refers to the resistivity times the thickness of tunnel junction, which should be in principle constant for all the devices. So the resistivity seems to be independent of size. There is a size effect on the on-off ratio. For the octagons, the on-off ratio drops from 18 for 10 micrometers to 5.3 for 1 micrometer, which is also quite good, and it is actually an achievement that we can make good devices scaling down to 1 micrometer. And comparing all the 2 micrometer devices, octagon is always the best and star seems to be the worst. With all these octagonal devices, we can study the resistance switching and different timescales. Here are the plots of R times A as a function of pulse number. To save some time, here we just do it like this, representing the synaptic depression and potentiation stage in neuromorphic engineering. Resistance is programmed with these pulses. At very fast pulses, like 20 nanoseconds here, probably the energy is insufficient to fully switch the biggest device, which is 13 micrometer, representing by the gray curve here. However, at longer pulses, it is almost size independent. As we can see, the red curves for 2 micrometer devices are shifted. To explain this, probably the real area of 2 micron devices are a bit underestimated. And we could also find a jump in the resistance for ultra-fast switching regime. However, it is only observable for the smallest devices, like the 2 micron device here, suggesting that there's also a scaling effect. And in terms of the on-off ratio, probably a moderate pulse width gives the best on-off ratio, so not too fast, not too slow. Finally, if we go back to our mask, we can see that we designed some structures together like XR and XC. And the idea is to co-integrate the ferroelectric tunnel junction as a resistor R and feed cap as a capacitor C together to build an RC circuit. Here is a three-dimensional view of the co-integration. Basically, for a capacitor, it requires a rather thick ferroelectric layer to store the charges. However, for ferroelectric tunnel junction, the HCl superlattice here should be ultra-thin to allow for tunneling. So we have to make a two-level structure. And with an RC delay line, we can connect the ferroelectric tunnel junction as a resistor in series of the capacitor together by marrying between paths A and C. This work is also heavily on cleanroom fabrication, and I made a short video on how we process the chip. So basically, we started with a layer stack containing an ultra-thin HCl superlattice on top of tungsten oxide as bottom electrode. Then we can pattern the mesa by e-beam lithography, and we can etch the via by direct laser writer. The next step is to define the bottom electrode by ICP2 etching into islands, followed by silica sputtering to protect the structure. Next, we deposited a tungsten pad, and we define the top pad. So we have the ferroelectric tunnel junctions ready. At this point, we perform many electrical measurements for the FTGs, and once we are happy with our results, then we decided to proceed to the feed cap, and we deposited the layer stack and pattern the mesa. That is where we are. We haven't completed the whole structure yet. To sum up, during my master thesis stage, we identified that molecular beam epitaxy grown VO2 is more robust for interfacing with HCl superlattice. And in terms of ferroelectricity, HCl superlattice reacts differently with VO2 and tungsten oxide as bottom electrode. And we designed and fabricated ferroelectric tunnel junctions with good scalability and on-off ratio down to 1 micrometer. Scaling is beneficial for operation at fast time frame, and also beneficial for energy cost. We figured out that octagon is the optimal shape for device operation, and finally, we designed a fancy mux for co-integration of tunnel junctions and capacitors. Future work could be addressed on checking the metal insulator transition of the vanadium oxide. And we could also try to incorporate a tungsten oxide layer in between the VO2 and HCl superlattice as an oxygen supplier. And in our lab, we have a better SMU, and during my master thesis stage, I spent a lot of time on setting up the probe station in our lab, so hopefully we could make more accurate measurements in the future. We can do more temperature-dependent measurements to study the transport mechanisms and to explain the weird step we observed. And we should complete the co-integration shape and try putting ferroelectric tunnel junctions on top. Okay, that's the end of my talk. Thanks for watching.